Hi and welcome to this second clip on basic organic chemistry, which goes through isomers and functional groups. So an isomer in general terms is a version of a compound which has the same molecular formula, but other aspects of its structure may be different in some way. So the type of isomerism that this clip will focus on is called structural isomerism. And this is defined as two versions of a compound which have the same molecular formula but different structural formulae. So not all compounds exhibit isomerism, but in general terms, the larger a molecule, obviously, the greater the different number of ways its atoms could be arranged. So here we've got the molecular formulae of the first 5 members of the alkane homologous series. So pause the clip and see if you can write out the structural formulae for all the different ways each molecule could be arranged. And think about what you notice as you complete this. So starting with methane, you can only write it as CH4. And you can write out its displayed formula to prove that. Likewise, you can do the same for ethane. There's only one way really of representing 2 carbons and 6 hydrogens. When you get to CH3, CH2, CH3, you could be tempted to arrange the carbons in a triangle to get a different arrangement of atoms, in other words, a different structural formula. The problem is that that now isn't C3H8 anymore, it's C3H6. So we can consider that an isomer. It doesn't match the definition of a structural isomer that's further up on the screen. In fact, it's not until you get to butane where you start to get structural isomerism showing itself. And in fact, you also give the isomers different names, because the second isomer actually is propane with a methyl group on the second carbon. You don't want to call it 2-methylpropane because there's only one place that the methyl group could sit. This can be demonstrated by drawing out the displayed formula for each of these. But you can see the difference. Now it's also worth pointing out at this stage, a methylpropane has less surface points of contact compared to butane, so less London forces exist. And what this leads to is methylpropane having a lower boiling point than butane, because it takes less energy to overcome the London forces in methylpropane. In fact, we can take it as far as saying more branched isomers always have lower boiling points than lesser or unbranched ones for this very reason, which will be illustrated when we look at pentane. So here's a little exercise for you to do. Pause the clip and you need to draw out the skeletal formulae of isomer A, B and C, and then rank them in order of increasing boiling point with a reason for your decision. And when you've done that, we'll resume the clip and we can see if we're in agreement. So first of all, we've got A, B and C. C can actually be drawn out in 4 different ways to say the same thing. And although we didn't actually ask you to give the names, there they are, just so we can keep on top of that side of it. So pentane is A, 2,2-dimethylpropane is B, and 2-methylbutane is C. So the order of increasing boiling point is B is the lowest, then C, then A, because increasing surface points of contact for more London forces, so more energy required to overcome the intermolecular forces. The reason is not there is more branching, because just saying there is more branching doesn't relate it to the idea of energy being required to overcome the intermolecular forces, which has a direct impact on the boiling point. So be very careful when you're doing explanations about this kind of thing, that you don't just say more branching. You need to make reference to the surface points of contact for more London forces, so more energy required. You need to relate it directly to what actually affects the boiling point, which is the energy requirement for overcoming the intermolecular forces. So a functional group is an atom or group of atoms which, when bonded to an organic carbon skeleton, will change the chemical behaviour of the molecule. So let's take an example. Let's take the simplest organic compound, which is methane. Now if we draw it out in displayed form, any one or more of the hydrogen atoms that are on the molecule could be substituted for another atom or group of atoms. So I'll show you some examples. So not only does it change the name, but it also changes the homologous series that each of these belong to. Now all of these homologous series you'll come across during your course, and others. This is not the only set of functional groups that you'll come across, it just serves to illustrate what a functional group is. So each of these will have their own specific sets of chemical reactions that they take part in, which the others won't. They may even have different physical properties to each other, because obviously some of them will introduce things like hydrogen bonding, as well as London forces. Others might introduce permanent dipole-dipole interactions, as well as London forces. So this is important to bear in mind too. So now it's time for you to do a little bit of thinking, not just about what this clip has been talking about, but also about some areas we've done over the last term or so. So some of these are going to have a synoptic element to them. This is going to be the way they'll ask you about this in exams. They'll spread their questioning over several topic areas. So we'll have some work on isomers, some work on general formulae, some work on intermolecular forces, and also some work on shapes of molecules, all of which we've done. So have a think about these, pause the clip and give them a go, and then come back when you think you might have some answers. So for the first one, we've got the HCH bond angle is 109.5 tetrahedral, because there's 4 bonding pairs and no lone pairs. With the COH bond, it's non-linear, 104.5, because around the central oxygen atom there are 2 lone pairs and 2 bond pairs. And in the final HNH bond, there's a lone pair and 3 bonding pairs around the central nitrogen atom, so therefore this will be trigonal pyramidal and 107 degrees. So moving along to the 2 alcohols, the second alcohol has 2 OH groups, so twice as much hydrogen bonding can occur, therefore it has the higher boiling point. In the case of the third exercise, you can easily use the molecular formulae to work out the algebraic relationship between carbon, hydrogen and oxygen. So 1 carbon, 4 hydrogens is CnH2n plus 2, just like methane. But there's an oxygen as well, so therefore CnH2n plus 2O. In the case of ethanol, beg your pardon, second one, C2H6O. So this one would be N is 2. There are 6 hydrogens, so that's 2N plus 2, and 1 oxygen, so CnH2n plus 2O again. Okay, so hopefully this has been reasonably helpful to just get you moving along with isomers and functional groups and what they're all about. Obviously, these exercises were designed to show you some of the context in which the exam board might ask you at A level, as well as giving you some examples to have a think about. So as always, the message is to go away and practice some of these to get your head around it and get used to it. So thanks a lot for listening, and until next time, see you soon.